Okay. Um, all right. Hi, hello. Uh, Today I tried to record. Today's session is going to be on heat. I've actually already recorded it. I'm recording this thing again because I had a lot of interruptions today. I couldn't record things properly. Actually, what happened was that I had my friend's hotspot turned out outside, and what happened was that first of all my laptop got connected to that hotspot which is very fast, so his connection is loose. But then I again used my own phone's internet connection to use on my laptop, but unfortunately I didn't check that my phone itself is again like its wi-fi is on and it's getting connected to his wi-fi. So today's recording might be muffled. Surely the video would be lagging and the screen share as well. But usually, what I've seen is that the audio is pretty okay. Uh, Still, I might just can I just take you guys through everything just as an overview so that I'll just show you what all did I discuss today. So today's topic was heat exchangers. I discussed a few equations. How is the overall thermal resistance calculated 1 over UA? What happens in the case of foiling? This is how a typical heat exchanger looks, right? Um, Now, for all the problems, we usually use two equations. One is surely the heat exchange rate. Whatever heat the cool fluid gains is equal to the amount of heat which the hot fluid loses, right? So from these two equations, we usually use one of these. And then secondly, we use LMTD or the effectiveness NTU method. We use LMTD if we know all the inlet and outlet temperatures of the hot fluid as well as the cold fluid. Just in case we don't know any of the values or we cannot determine even using this, then in that case, we use the effectiveness NTU method. Now, what is the effectiveness of the heat exchanger? It is Q dot over Q max. Q max is C min times TH in minus TC in. What is for the effectiveness LT, as for the LMTD method, we have Q dot is U times AS times delta T LMTD. Now delta TLM is delta T1 minus delta T2 over ln of delta T1 minus delta T2. What is delta T1? It is the temperature difference at the inlet. Let's assume 1 is the inlet, okay? Inlet for fluid 1. So at inlet of fluid 1, at that point, whatever is the temperature difference between the two fluids, at that specific point, and what is delta T2 at the outlet of the colder fluid. What is the temperature difference between the two fluids? That is delta T2. That is how you get delta TLM. And we have a factor which comes in just in case we have cross flow. I discussed two problems. One is using the um, LMTD methods. This one is using delta TLM. And the other one uses the effectiveness NT method. I did not properly prepare for this session today. I couldn't, and my apologies for that. Because let's leave the because. But the thing is, I chose problems randomly 11.23 and 11.35. So 2.3 had this issue that 2.3 was okay. 3.5 had this issue that it used an even complex method for calculating the effect using the effectiveness NT method to calculate the outlet temperature of the cold fluid. So because of that, I had to simplify things a bit here because they used K dash L and the eta naught values, which even I'm not used to use it. So I do not have the final answer to this problem, but I do have the final answer to this problem. So, but I have explained these steps clearly. Hopefully, it's okay, and hopefully everyone gets uh, the overall understanding of the heat exchangers. For me personally, heat exchangers is one of the most simple topics in this module, which I've like seen overall in terms of problems specifically, and radiation as well. But we'll see that later. So that's it. Please enjoy the video today. To this clip, I'm going to append the clip which I recorded previously, and that is going to be muffled and a bit laggy. So next time I'll make sure that my Wi-Fi is turned off while I'm using my phone's hotspot to give internet to my computer. That's it. Thank you. Stop. Stop share as well. And let's. Okay, so I'm recording. Let's share the screen. So I hope the screen is there and I'm audible as well as visible. And the topic which we are going to discuss today is heat exchangers. This is the area which I had done my initial preliminary research during my bachelor's. And currently, my current research topic is also a bit related to heat exchangers only. It's related to cold box very specifically. Anyways, let's begin. So, uh, heat exchangers are typically, so I'll just take a pic from here. This is how typically heat exchangers look like. So they have heat exchangers are basically used to transfer heat from one fluid to the another. Usually both are fluids, none of them are solids. And in this case, what we see is we have a hot steam at 50 degrees Celsius. Steam at 50 degrees is a bit controversial because uh, steam is always steam only when the temperature is above 100, but they might have changed the pressure or something in this problem. I'm not very sure. Anyways, so we have a hot steam coming in from the top, and then the steam leaves as well. And we have water running inside this small pipe which goes inside this heat exchanger. Uh, and water gets heated up due to the presence of steam. So this is how the typical heat exchanger works. I could go and discuss about how to derive the formulas as well, but I think I'm just going to go through the summary and then discuss a few problems. Today, I couldn't spare time to select a few problems which I'm going to discuss, so I'm just going to randomly choose and hopefully I'll be able to solve it properly. I mean, I have the final answers for sure for all the problems, so surely I won't give you a wrong uh, answer, but maybe I might make a mistake during solving the problem. Anyways, so typically the overall heat, the overall thermal, okay, there are a few terms. There is thermal resistance, okay, and there is uh, you can say the overall thermal heat transfer coefficient as well. But let's use thermal resistance as of now, okay, which is represented by U. So the overall heat transfer coefficient whenever we have a heat exchanger is defined like this: 1 over U times AS is 1 over UI times AI uh, is equal to 1 over UO times AO, which is equal to R, which is the total thermal resistance, uh, which is 1 over, this is represented by R, which is 1 over HIAI plus resistance of the wall plus 1 over H out A out. Now, IE here stands for the inner surface and O is the outer surface. Okay. Uh, Now, in this case, usually in heat exchangers, they assume that the thickness of the wall is very, very small. So this this thickness, not this tiny thickness of the wall is very tiny. So in that case, what happens is that we can ignore this thing. And AI is also almost going to be equal to AO, which we can say is equal to AS. Okay. So we typically use this assumption and then we say 1 over U is almost equal to 1 over HI plus 1 over HO because the terms cancel out. The area cancels out, this turns out to be 0, and that's how we derive it. Okay. Um, so overall resistance in that case can be derived using this formula. 1 over UIAI equals 1 over UOAO equals R. Okay. Uh, just in case there is some fouling happening. So if there is some fouling which happens, so whenever the heat exchangers are used again and again in cycles, uh, there is some fouling, some layer of minerals forms near the wall, which causes more resistance in heat exchange. So slowly the performance of the heat exchanger decreases. At the like the first operation of the heat exchanger would be the one which gives us the maximum heat transfer and then slowly degrades. So if there is some fouling happening inside the heat exchanger, it is going to have its own effect, which is so in that case, if we have fouling, we are going to say 1 over U times AS equals 1 over UIAI equals 1 over UOAO equals R. This we know, right? Now this R in the presence of fouling would be 1 over HIAI plus RF inside over AI. So this is the fouling resistance, RF inside plus ln of D naught over DI over 2 pi KL. This is the thermal resistance due to the thickness of the wall. Plus, we can say RFO over AO plus 1 over HOAO. Right? So these two terms came due to the fouling, and this term came due to the R wall basically. So this is how we define the thermal resistance in the case of fouling. Okay. Uh, so what after this? So if we assume that if we I need a little bit thicker. Okay. If we assume that heat exchanger is fully insulated, which is like practically this doesn't happen, but we can assume this for simplicity of our solutions. If we assume this, then we can say that the overall heat which the cold fluid gains is equal to the amount of heat which the hot fluid loses, right? So Q dot is the overall heat exchange rate is M dot C. C is cold. Then Cp of C times Tc out minus Tc in. Uh, so you can also say it is Cc times Tc out minus Tc in, right? Because the cold fluid is getting heated. So that is why we say out minus in, right? If we write the same equation in terms of the uh, hotter fluid, we are going to say Q dot is M dot H, what term? H, right? Okay. M dot H CPH times TH in minus TH out because the hot fluid is going to lose heat is equal to CH times TH in minus TH out, right? Very simple. And then in most of the problems, we just equate these two to get one one equation, and then the other equation we get from LMTD or effectiveness NTU method. So what are these? Again, I cannot discuss it right now, but hopefully you guys know. If not, go through the lecture slides and you'll get a hang of it. Now there are two methods used for the heat exchanger problems. One is the so if we have for problems, we usually need two equations. Okay, first equation comes from this. Usually, I mean, majority of the times. The second equation comes from LMTD or effectiveness NTU method. NTU here stands for Nanyang Technological University, right? Number of effective units, number of transfer units. So, but when do we use LMTD? We use LMTD for if we know all inlet outlet temperatures. When do we use effectiveness NTU method? I'm going to say otherwise. In all other cases, we have to use the effectiveness NTU method. So probably I'll take one problem from LMTD and one problem from ENTU method, and then we'll call it a day after this is done. Okay. Now, if we are okay, so a bit about these two methods as well. So if we are using LMTD, then uh, the heat transfer rate Q dot is U times AS times delta T LMTD. Okay. Now, what is delta T LMTD? Usually, they don't write delta T LMTD. They just write delta T LM. Okay. So now, what is delta T LM? Delta T LM is delta T1 minus delta T2 over ln of delta T1 over delta T2. Now, what is delta T1? What is delta T2? At point one, at any point, basically, it could be inlet for one and outlet for the other. If there is like a cross heat exchanger, but it might be same as well. Usually, they keep opposite because the heat exchange rate is higher. Anyways, so delta T1 is at any point what is the difference between the temperatures of the two fluids, either entry or exit of any one. Uh, and delta T2 is at the other point, what is the temperature difference between the two fluids? That is how we get delta TLM using this formula. Now, okay, what next? Okay, if just in case we have cross flow, okay, if we have cross flow, then delta TLM would be F times delta TLM of cross flow. So this is how this formula we can use just in case we have cross flow. Now, what is F? F is the correction factor. How do we get it? People have determined experimentally using different cases. Usually that will be given in the problem. You cannot determine that. They might also ask you to look up into the tables and then find out what is the value of F. I think probably there might be a list. I did not check. Uh, but basically you will know if there is like F value you cannot determine. Or they might give you both the things and then might ask you to calculate it. Okay. Next thing is effectiveness. So another formula. So effectiveness of heat exchanger represented by epsilon is Q dot over Q max, which is how much heat exchange is taking place over how much heat exchange is possible at the maximum. Maximum would be when all the heated fluid is always coming in touch with the coldest part of cold fluid. Uh, I think better to represent this in an equation format so that you'll get a hang of it. Just try to think after I write the equation. So, uh, what is Q dot max? Q dot max is C minimum times TH in minus TC in. TH in is the temperature at which the hot fluid enters, which is the highest temperature inside the heat exchanger. TC in is the lowest temperature inside the heat exchanger. So just in case every heat transfer which is taking place is at this temperature range, then this is how we get the Q dot max. Please be aware, here we are using C min. That means whichever has lower C, M dot Cp, okay? C min means it could be M dot H CPH or M dot C CPC. We use a minimum of this. Okay, my handwriting is minimum of these two. That is how we get Q dot max. Okay. Okay. What after this? I think that's it. Now I'll come to the problems. I'll take maybe 5 minutes to decide which two problems do I want to take up because let's not take from a textbook. Let's take it from Incropera, okay? Because I like that book. Yes. There are a few sections which I see. One is overall heat transfer coefficient. Okay, we'll take a problem from this. We'll take probably 11.4. So 11.4 and which one? Okay, we'll take 11.18 because this is related to fouling. And then maybe a few about LMTD and ENTU if they give any. Let's see. There are so many problems. Additional considerations. So probably I'll take one more problem in that. Also, I might skip because I have less time today. But okay, let's see. Let's find a good problem and then notion from the energy conversion system is being proposed, such as give me a sec. I think 11.23. Let me look up LMTD problem. Hmm. 11.23 looks good. Pick up 11.23. One more, maybe. Let's see. Okay, 11.35. I think that's all. I might even skip. I don't want to skip 2, 3, and 3, 5 because these are LMTD and ENTU methods specifically. Maybe I'll skip 4 and 18 and let's just go for these two problems. I think that would be better. 11.23 and 35. Okay. So 11.23. Oh, did I not check host tools and then turn off the waiting room? So 11.23, right? It's getting too hot for me. Just so 11.23. I hope this diagram is from that. A concentric tube. Okay, let me paste it here. Okay. So 11.23 states a concentric tube heat exchanger for cooling lubricating oil is composed of a thin walled inner tube of 25 diameter carrying water and an out. Okay, so inside tube is carrying water and the outer tube of 45 diameter is carrying the oil. Okay, outside is oil. The exchanger operates in counterflow, so there is counterflow. There will be F involved, the factor, with an overall heat transfer coefficient of 60. So H overall is, we know, it is 60. Uh, and average properties are given. So we have the properties of oil and water. We have rho, Cp, nu, K, Prandtl number. Okay. What are they asking us to calculate? They want us to, if the outlet temperature of the oil is 60 degrees, determine the total heat transfer and the outlet temperature of water. Okay. Just take 2 minutes and then think on the problem. I'll just start in 2 minutes. So I'm having some issues with the Zoom software or my internet connection. I'm not very sure. Probably my internet too. Let me share my screen. I'm, I'm pretty sure that I'm not very sure if the previous part was recorded or not, but I discussed a lot about the basic theory of heat exchangers, and uh, then I decided on which problems am I going to discuss today. Okay, I'm back again, and today my internet is very shitty. I'm not very sure why. So I'll just continue with the problem. I'm just going to ignore whatever happened, whatever got recorded, whatever did not get recorded. Because I think it keeps on happening again and again. Okay, so red is oil and black is water. Water initially enters the system at how much? So we can say TH out. Oil is the hotter fluid, and when it comes out at 60 degrees Celsius. This is what we have been given. And water goes in. So TCI is 30 degrees Celsius. And is there anything else that we have? Concentric tube, thin walled membrane. Okay, TO in B. We also have this. Okay. So we have TH in as well. Right? It is 100 degrees Celsius, but we don't know this, right? We don't know TC out. This is going to be a very simple heat exchange. We are going to assume that it's fully insulated. And let's just use a simple energy balance equation. Okay. So using all energy is Zoom there with me? No, is Zoom is there. But I did not share my screen. Okay. Okay. Now my screen is there, hopefully. So this is how I'm drawing the circuit diagram. And now I'm saying I'm going to use the overall energy balance equation. What is that? You just equate the heat lost by the forward to the gain by the cold. Just so you can say Q dot is M dot CPH TH in minus TH out, which is equal to M dot C times CPC times TC out minus TC in, right? Now, what is M dot of H? M dot H is 0.1, which is equal to M dot C as well. So Both are having the same mass flow rate, but different densities and different CPs. So let's cancel out the m dot terms because both are same. Uh, After this, we can say CPH is 1900 times H in is 100 minus H out is 60, which is equal to CPC, which is 4200 of water, and out minus 30 degrees Celsius, right? If you calculate using this, the answer which I have is, how much do I have? TC comma out is 48.1 degrees Celsius. Simple linear equation to solve to get this. Now think, we have THO, we have THI, we have TCI, we have TCO. Which method to use? There is still some problem to solve. I haven't even looked into what is the next part. Okay, now I just had a look. It says determine the length required for the heat exchanger for this temperature difference. So what are we going to use? We are going to use the LMTD method and not the effectiveness NTU method because we know all the four temperatures, right? So now let's quickly do it. Okay. Heat exchanger is one of the simplest parts of this module as per like best of my understanding. At least I find it very, very simple. Things are very direct and very simple. Okay, so LMTD, right? Right here. So for LMTD, what are we going to use? We can say that Q is U is A times uh, delta T LM for the counter flow, right? Which is equal to U times pi d L times, because this is the area, pi times d times L, LM for the counter flow. So from this, we can say that L is Q over times Q times pi d times delta T LMCF. Delta T LM counter. This is what we got. We are going to call this equation 1. This is equation 2. And let's move. Now delta T. So delta T. How do we the formula for the counter flow? Delta Apologies, my Zoom is disconnected, crashing a lot today. 100 minus 60, I think. Okay, yes, which is uh, 0 watt is equal to Q. Now, you all these values, I think we're just going using one, substitute the values, okay? L is, what is Q? 7600. What is U? We don't know. We know. Um, I think it's given, right? The overall heat transfer coefficient of 60. Okay, so we have U. We have 60 times pi. What is the D value? Because we have two things here. One is the inner diameter is 25, the outer is 45. How much do you think? Which one is D? It's always the wall from which the heat exchange is taking place, which is the inner wall, right? So we are going to take D as 25 mm. So 0.025 times what is delta TLN? It is 40 degrees, right? So am I seeing? The Zoom is testing my patience. I just used all the because this is the part A of the problem is done. Now you might think that how is the 0.3 even possible? I mean, if you create a heat exchanger which is like 40 meters in length, it's like it's going to take it a lot of space, right? That is why we have heat exchangers. So they do not go like it's not 40 meters like this. It's like this, like a maze. Okay, goes down slowly, slowly, slowly. This is how we get 40 meters, but within let's say half a meter. Because usually the heat exchangers which I have seen, shell and tube heat exchangers majorly, they're going to have lots of tubes, not just in two Bs. It's all like a gun barrel. So a lot of tubes are inside, and that's how they get even 40.3 meters as the length because they have multiple such tubes. So even if they have like 80 tubes, it's going to take half a meter, right? Assuming we take only horizontal lengths. If we take the turning area as well, that's going to reduce even more. But then there is fouling, which happens. So we almost get an approximate answer usually. Okay, and that's it. Determine the length required for the problem. Now, using the effectiveness NTU method, or we can solve this one as well using the effectiveness NTU method. But let's go for the next problem, which is 11.35. So what is the problem? 11.35 looked interesting to me. That's why I chose this. It has a diagram and it says you have to specifically employ the effectiveness NTU method. So that's why I chose this one. All right. So this is 1.35. A counterflow twin tube heat exchanger is made by brazing two circular nickel tubes, each 40 mm long. Okay. 40 meters long. Okay. Together, as shown below, hot water flows through the smaller tube of 10 mm diameter, and air at atmospheric pressure flows through the larger tube of 30 mm diameter. So below we have air, outside we have water. It is a counterflow. Both tubes have wall thickness of 2 mm. Okay. And there is a raising joint in between. So thermal contact conductance per unit length of the brazed joint is 100 watt per meter Kelvin. Contact conductance. Okay. I think they should write resistance here because they are writing watt per meter Kelvin, right? No, it's K. So it's okay. Yeah. K is watt per meter Kelvin. The mass flow rate of the water and air 0.4 and 0.12. The inlet temperature of the water and air is given 85 and 23. Employ the effectiveness ND method to determine the outlet temperature of the air. Okay, and they are also giving a hint account for the effects of the circumferential conduction in the walls of the tubes by treating them as extended surfaces. Okay, I'll give you 1 2 minutes to think over this and then I'll begin. Meanwhile, I'll just pull up the final answer here in front of me. So, okay, we will have to use a few properties as well, from where you will have to either they will be given to you during the problem. If then I don't know, God will help you. Anyways, so we have even I have to read the problem once. Okay, so let's draw it together this time. Let me use a blue pen for the colder fluid. This time sky blue. So and this is TC in. How much is TC in? Have they given us? 23 degrees Celsius. What is TC out? We don't know. Now let's use a red pen for the hot fluid. Because there's a counter flow, it flows opposite. And TH not out, but is how much is it? 85 degrees Celsius, right? 85 degrees Celsius. And M dot H is 0.04 and M dot C is 0.12, right? This is all what we have been given. So now, box here looks pretty, right? Mm. There might be an option to draw some. Okay, there was a shape. Never mind. Next time. So this is the system which we have, right? And this one is air, and this one is water, right? So we'll directly use the effectiveness NTU method because told that you have to use. In effectiveness NTU method, how do we begin it? We begin it by directly writing down the equation. So epsilon is 1 minus E, or let me write exp, which is e raised to the power minus NTU times 1 minus CR over 1 minus CR e raised to the power minus NTU times 1 minus CR, right? Hmm. And what is NTU? Nanyang Technological University, right? UA over Cmin. And what is CR? CR is Cmin over Cmax. Now Cmin, Cmax, you have to calculate it for all, for the heat, hot fluid and the cool fluid, and then you have to check which one is minimum, which one is maximum. So basically CR is less than one. That's how I usually think. Um, Now they want us to estimate the determine the outlet temperature of the air. Okay. First of all, we can, I think, using the um, we so there is another formula for effectiveness, right, which we discussed. Effectiveness is CC of TCO minus TCI over C min of THI minus TCI, right? This is the maximum heat transfer possible, and this is the heat transfer which actually takes place. You can also write here, instead of CC TCO minus TCI, you could have written CH THI minus THO as well, because both are the same because of the heat exchange and assuming that there is in everything is insulated here, right? So we have these two formulas. Now, from the water side, okay, we in this case, because we do not know exactly what is, we need to calculate the heat transfer coefficient. That is the, for both the fluids, we need to calculate the heat transfer coefficient. Using that, we'll be able to calculate U, and from that we can use the effectiveness formula. So now how does this problem flow? You have to calculate the Reynolds number to check if the flow is turbulent or how the flow is. Okay. Now water is rho Vd over mu, right? Rho Vd over mu, which you can also say 4 times m dot, water is water fluid, right? 4 times m dot h over pi du. How I got this? Just think, just calculate a few, cancel out a few terms, and you'll get to know. So this is 4 times 0.04 over pi times, what is d for water is 0.01, right? 0.01 times what is u? Mu. This is not u, this is mu. That is what I was thinking. Now, mu value you're going to get for water from this table. So for water, mu is 453 times 10 to the power minus 6. 453 times 10 to the power minus 6. Okay. So from this, you're going to get RE as 11243. So surely turbulent flow, right? Water is turbulent. So for the turbulent flow, we use the Dittus-Boyler correlation, which states that Nu is Hd over K, right? H of the outer fluid times D of the outer fluid over K. Now, if you the Dittus-Boyler correlation states that this is equal to 0.023 times Re raised to the power zero point 0.8 times Prandtl number raised to the power zero point 0.3. From where did I get this? Go back to the data handbook and you'll be able to find this correlation. Now, using this, we can say that it is 0.023 times 11243 again. I'll try and fix this from the next time. So, okay, 11243 raised to the power zero point 0.8 times what is the Prandtl number? That also, I think, should be there. 2.88, right? So 2.88 raised to the power zero point 0.3. The value which I have here is 54.99. Okay. Now using this, can we get H? We can surely get H, right? So from this, we can say H of outer is 54.99 times what is K? K is here 0.656. 0.656 over B, which is 0.01. So HO, the value which I have is 3607 watt per meter square Kelvin. This is the outside heat transfer coefficient. Now, what is the similarly we are going to do for air as well? Very similarly, okay. So we will say RE of air is rho VD over mu, which is 4 times m dot C over pi d mu, which is 4 times what is m dot 0.12 over pi times what is d for this? D 0.03 times what is mu? Mu for air is 184.6 10 to the power minus 7. 184.6 E minus 7, right? Which is 275890. Such a big value. This is what I have. That again means turbulent. Now, once we know turbulent, we are going to use Boilter correlation, right? So we'll say Nu is H inside times D over K, which is 0.023 times Re raised to the power zero point 0.8 times raised to the power zero point 0.3, which is 0.023 times 275890 raised to the power zero point 0.8 times what is the Prandtl number for air? 0.707. 0.707 raised to the power zero point 0.3, right? The value which I have for this is 450.9. Okay. Now, from all this, we can calculate H inside as 450.9 times K. K is how much is the K for air? It's less 0.0263. 0.0263 over how much is D? D is 0.03, right? So we can say HI is 395.3 watt per meter square degree Celsius or Kelvin. So this is the value of heat transfer, the inside heat transfer coefficient. Now from this, how do we calculate the overall heat transfer coefficient? Um, single thing. So the I mean, I'm going to solve it from the simplified point of view and not the complicated point of view. The complicated way is to, I just speak a bit about it. 1 over UA is 1 over eta naught times HA of the water fluid plus 1 over K dash T times L plus 1 over eta naught HA of the cold. Now, eta naught and K dash T, these have come in because we do not have simplified heat exchanger, not simplified heat exchanger. These things have not been discussed in your textbooks. That is why I don't want to pull it up. Even I'm not rehearsed for this. Although I know this equation, I have read this before, but like I'm not prepared for this solving this equation. I could still do it. I mean, I we could give it a try. The thing is that we do not have a very simplified heat exchanger here, right? We have a brazed joint and we have two circular tubes which are connected through these brazed joint, and that joint also has some length. That is why all these complications are coming in, because we cannot simply use the K. We have to use K dash L because now the whole surface area of the nickel is being used for heat transfer. Similarly, because the tubes are not completely concentric, that is why we have to use eta naught, which is not bringing up the complete area which comes into the picture if the tubes would have been concentric. So we are using just some part of the tube, and also because of brazing, we have K dash T, which is some part of that nickel is causing the conductance between the two, the heat conduction between the two fluids. So, anyways, I think I'm just gonna pull in the values of these two terms. Or I think better that, so if so the simplified form of this, simplified form of this problem, that means I do not have the final answer for you guys, but at least you'll know how to proceed, is we simply use 1 over UA is 1 over HA of water fluid plus 1 over KL plus 1 over HA of the cool fluid, right? KL we can know from the how much is the length of the nickel and how much is the conductivity of nickel. H of H we know. A of H we also know how much is the area which is coming in contact due to the hotter fluid. H of C we also know because we just calculated it for air, right? Where is it? This one, 395.3, and we also know A of C. Now, once we have all these values, we will know what is UA. From this, we can get the value of UA, right? This thing. So once now we have UA, so we can simply say what is the equation for NTU? NTU is um, NTU is UA over C min, right? So from this we are going to get the value of NTU. Now once, okay, I'll just show. So from this, we are going to get the value of NTU. Now, once we have NTU, we also have CR always because we know the Cmin and Cmax, right? So we have CR, we have NTU. So we have everything for this. We have everything for this. And from that, we are going to calculate the effectiveness. Now, once we have the effectiveness, we have C of cold, we have C of min, we have THI, we have TCI as well, and we have TCI as well. So this is what TCO is what we can get, right? And what are they asking of water and air, thermal. So yes, that is how we get. I mean, this is what they want us to calculate, right? So see, very simple. From this, we have the value of UA, right? So get UA, then get NTU value, then get CR value on this R. Get CR value. From this, now once we have CR, once we have NTU, we are going to get the effectiveness value. Get effectiveness value. From this, get TC. This is the pattern which you have to follow to finally get TCO, right? I hope it makes sense. Okay, I think that is all for today. I'm already 18 minutes over my usual time. Let me stop sharing my screen and um, okay, I think that's it for today. Thank you very much for joining. I'll see you guys probably next week. I think we just have 2 or 3 sessions more remaining. After that, it's going to be a goodbye forever until we somehow get in touch. Okay, thank you. Bye.